Ever really stop to think about what's going on inside your phone when you tap that screen? Well, in this explainer, we're going to pull back the curtain and look at the tiny, tiny little switches that basically power our entire digital world. So let's start with a big question. How in the world do our devices actually think? I mean, how does your phone or your laptop process all that information and make billions, literally billions, of calculations every single second? The answer is actually pretty simple. It all boils down to these microscopic electronic switches called logic gates. The best way to think of them is like the atoms of computing. They work with the most basic information you can imagine. A signal is either on or it's off. And in computer speak, we just call an on state a 1 and an off state a 0. That's it. Every single thing your computer does, from loading a web page to playing a game, is built from these simple choices. Okay, so let's meet the 3 most important players in this game, the ones that form the foundation of, well, everything in digital logic: the AND, the OR, and the NOT gates. First up to the plate, we have the AND gate. I want you to imagine this gate is like a really, really strict bouncer at some exclusive club. To get past the velvet rope, you don't just have to be on one list, you have to be on both. So the rule for this bouncer, our AND gate, is simple and it is absolute. To get a high output, which is just another way of saying an on signal, or a 1, both of its inputs, let's call them A and B, must be 1. If even one of them is a 0, the gate just outputs a 0. No exceptions, doors closed. And we can map out every possible scenario for this gate using something called a truth table. Just look at it. Notice how that final column, the output, only shows a 1 in that very last row. That's the only time where both inputs, A times B, are 1. All right, next up, let's meet the OR gate. Now, if the AND gate is that strict bouncer, the OR gate is its much more easygoing friend. This gate's rule is super simple. It'll give you an on signal if input A is on, or if input B is on. And hey, if they're both on, that's great too. The door's wide open. Its truth table shows this perfectly. The only possible way to get a 0 out of this thing is if both inputs are 0. Any other combo, you're getting a 1. And finally, for our basic set, we have the simplest one of all, the NOT gate. People often call it an inverter, and you're about to see why. This one is just beautifully straightforward. It takes just one single input, and it flips it to the opposite state. It basically does the exact opposite of whatever you tell it to do. I mean, look at its truth table. It's the shortest one you can have. You put in a 0, you get a 1. You put in a 1, you get a 0. That is its entire job. Okay, so now that we've got the basics down, this is where things get really, really cool. Let's talk about the universal gates. Now, they're called that for a pretty powerful reason. You can build any other logic function, an AND, an OR, whatever you want, using only these gates. This makes them unbelievably efficient for designing circuits. So first is the NAND gate, which is literally a not AND. All it is an AND gate with a NOT gate stuck on the end of its output. It does the whole AND operation, and then it just inverts the final result. And its truth table is the exact opposite of the AND gates. Remember how the AND gate only gave us a 1 when both inputs were 1? Well, NAND does the complete reverse. That is the only time it will ever output a 0. Following that same pattern, we have the NOR gate, and I bet you can guess what it is. A NOT OR. It does the job of an OR gate and then immediately flips the outcome. This makes it the perfect opposite of the OR gate. So it only outputs a 1 in that one single case where both of its inputs are 0. All right, finally, let's look at a couple of specialist gates. So while those universal gates are all about efficiency, these guys are designed for very specific but incredibly common comparison jobs. The XOR gate, which stands for exclusive OR, is basically a difference detector. It's constantly asking one question: are my two inputs different from each other? And this makes it so useful in circuits that do things like arithmetic and error checking. You can see its special job right there in the truth table. The output is 1 only when the inputs A and B are different. If they're the same, whether they're both 0 or both 1, the output is 0. And of course, you've probably guessed it, the XNOR gate is the exact opposite. It's an exclusive NOR, or what you can call an equivalence detector. It asks, are my inputs identical? It only gives you a 1 when the inputs are exactly the same. So we've met all these individual gates, these tiny little decision makers. But how do we get from them to the incredibly sophisticated technology we use every single day? How do they build our world? Well, it's all about building up in layers, but at an almost unbelievable scale. We start with those simple on-off signals, the zeros and ones. Those signals feed into our logic gates to make tiny decisions. Then millions, or today even billions of these gates, are crammed together to form complex circuits that can do things like basic math. And then those circuits are assembled into microprocessors, the brains that power everything from our phones to our cars. The most amazing takeaway here is this: all the immense complexity of modern computing. I mean, everything from your phone to the internet to artificial intelligence, it's all built from these few, incredibly simple rules we've just talked about, which it just leaves us with a pretty fascinating question to ponder. If this logic built our digital world, what will the next logic build?